In this question, a student analysed a sample of ink that contains 2 different dyes and a sample of an unknown dye, X, using paper chromatography. Simplified versions of the chromatograms produced are provided alongside centimetre rulers. So if we have a look at the image here, we can see the procedure for chromatography is having a strip of paper, and at the bottom we have a pencil line drawn on with a drop of the ink on that line, and then it's dipped slightly into water, and as the water is absorbed by the paper and travels up the paper, the dye moves with it. And if we have multiple different types of dye in our ink, they are going to move different distances based on their different properties and become spread out. So we can see results with ink sample that was containing 2 dyes. We can see dyes A and B have spread out as they traveled up. And then we can also see our results with dye X separately. And we can see that dye X traveled up the paper as well. So first we're going to be finding the retention factor for each of the dyes in the ink sample. That's A and B. So to do that, we're looking at their solvent distance and component distance. The solvent distance is how far the water, in this case, traveled up the paper. So that's going to be here on our diagram. So that's going to be 8 centimeters for both A and B because they're on the same piece of paper. So our solvent distance was 8 centimeters. The component distance, that's how far that ink dot moved. So A is here, that's at 4 centimeters. B is here, that's at 2 centimeters. So our component distance for A was 4 centimeters, and our component distance for B was 2 centimeters. Finally, to calculate the retention factor, we can go to our reference sheet to have a look at the equation. Here's retention factor. Retention factor is the component distance divided by the solvent distance. So component distance divided by the solvent distance. So for dye A, that's going to be 4 divided by 8, which gives us 0.5 for dye A. And for dye B, that's going to be 2 divided by 8, which gets us 0.25 for dye B. And that retention factor tells us what fraction of the total solvent distance did our component travel. So you can see for dye A, it was half. Dye A made it halfway up the paper compared with where the water ended up. And for dye B, it's a quarter. Dye B ended up a quarter way up the paper from where the water ended up. Our last step is to compare our results with dye X to the results with the ink sample to determine which of these component dyes, A or B, is most likely to match up with dye X. Now, at first glance, you might think, well, dye X went to 2 centimeters, dye B went to 2 centimeters, so they're probably the same. However, the water went to a different level. The solvent distance for dye X in this particular experiment was only 4 centimeters. So if we think about the retention factor for dye X, it only went halfway up the solvent distance. So for X, the retention factor is going to be about half. And the retention factor is what determines which dye it is. So since our retention factor for X is about half, and dye A's retention factor is about half, dye X is most likely to be dye A. So our answer is dye A. The reason why is that it has a similar retention factor to dye X. So the retention factor is what is the property that kind of determines which dye we have, not the component distance that it's traveled and not the solvent distance. It's a combination of those in the retention factor.